So how can the simplest, most basic rule in logic, the kind of thing you learn on day one of a philosophy class, help us navigate a world that's just completely jam-packed with paradoxes and contradictions? Well, that's exactly what we're going to break down right now.
All right, let's get right into it. Logic? It's unbelievably powerful, right? It's the engine behind basically everything, science, computing, you name it. But, and this is a big but, it has this secret vulnerability, a single point of failure that can bring the whole thing crashing down.
And I'm not exaggerating here. What if just one tiny contradiction, one little statement that says something is both true and not true at the same time, could just invalidate everything? I know, it sounds super dramatic, but in the world of classical logic, that is the exact risk we're dealing with.
Yeah, there's actually a name for this, the principle of explosion. And the idea is both simple and honestly kind of terrifying. If you let just one single contradiction slip in and accept it as true, you can then logically prove, well, anything. Literally anything. That the sky is purple, that pigs can fly, that 2 + 2 is a billion. It's like a single typo in one line of code that crashes an entire operating system. The whole logical framework just becomes completely and utterly useless.
So the big question is, how do you protect logic from what is basically a built-in self-destruct button? Well, the answer, and you're not going to believe this, comes from the absolute simplest, most basic rule you can possibly imagine.
It's this: A equals A. The law of identity. A cat is a cat. A thing is itself. I know, it sounds almost silly, right? Trivial. But this is what's known as a tautology, a statement that's true no matter what. And that's the key. That's what gives it this absolute logical sense. It's like a fundamental constant of the universe, a perfectly stable anchor point we can build everything else on.
Okay, but here's the thing. A rule, even a perfect one, isn't quite enough on its own. To really make it powerful, it needs a specific place to do its work, a place where its absolute truth can be totally guaranteed, with no interference. And this, my friends, is where our secret weapon comes in.
It's called the interval of abstraction. And the best way to think about it is like the lines on a tennis court. Inside those lines, the rules are absolute, right? A ball is either in or out. There's no maybe. Well, this interval does the same thing for logic. It creates a contained safe zone. It draws a boundary and says, okay, inside this box, within this context, our rules apply perfectly. It seals it off from all the messiness and gray areas of the real world.
And what this does is actually pretty brilliant. This safe zone lets two different kinds of identity exist at the same time, peacefully. Inside our little logical box, we have absolute identity. A equals A, always. No exceptions, no questions asked. But outside in the real world, we're dealing with relative identity. Think about it. Are you the exact same person you were 10 years ago? Well, kinda. It's vague, right? It's inconsistent. This framework lets us have both. We get to keep our perfect, pure logic and acknowledge messy reality.
Okay, so let's recap. We have our hero, the super simple rule, A equals A. And we have its fortress of solitude, the interval of abstraction. Now let's see how these two things team up to disarm those system-destroying contradictions we were so worried about at the beginning. And here's the crucial insight. Instead of a contradiction causing that big, catastrophic explosion, it gets transformed. It's not just a simple case of this is true and not true anymore. Now, it's a question of context. We have to ask, are we looking at this from inside our defined logical safe zone or from the outside? So the contradiction doesn't break the system. It just forces us to be clear about our perspective. So here's how it works in practice, step by step. First, the system flags a potential contradiction. Something looks off. But instead of freaking out, it goes to step 2 and asks a really smart question. Hey, is the A in the first part of the statement really, truly identical to the A in the second part? Then comes the most important part, step 3. Does this claim of identity fall within our predefined safe zone? And if the answer is no, boom, step 4 kicks in. The contradiction isn't a real system-destroying one, it's just apparent. And just like that, the explosion is totally avoided. Okay, I know this might all sound a little abstract. So let's make it concrete. Let's apply this whole idea to a classic real-world paradox that has had philosophers and logicians scratching their heads for a long, long time. We're talking about Poincaré's paradox, and it all comes down to the problem of vagueness. Normally in logic, if A is like B and B is like C, then it follows that A has to be like C. That's a rule called transitivity. But what Poincaré's paradox shows us is how this simple common-sense rule can completely fall apart in the real world.
Check this out. A perfect example is with color swatches. So look at swatch A. It's nearly identical to swatch B. I mean, you can barely tell them apart. And swatch B is nearly identical to C. Makes sense. But then you put swatch A right next to swatch C, and whoa, they are clearly different colors. Our whole chain of almost the same just broke. That clean, logical rule of transitivity, poof, gone.
So how on earth do we fix this? You guessed it, we use our tool. By creating one of those intervals of abstraction, we can build a specialized kind of logic just for this problem, a logic of indiscernibilities. It uses this really cool idea called metric equality. Basically, it's just a way of saying, look, if the difference between two colors is smaller than some amount we agree on beforehand, then for our purposes, we're just going to call them identical. It sets a clear boundary for what counts as the same. So the paradox doesn't break the system. The system just adapts to handle the fuzziness of the real world.
And this all brings us to the really big idea here, the so what of it all. What does this actually mean for how we understand the world around us?
So why does any of this matter? Because it takes logic from being this brittle all-or-nothing system and transforms it into a flexible, adaptive tool. It means we can build systems that can actually handle the vague, inconsistent, blurry stuff that makes up our complex reality. It finally bridges the gap between the world of perfect, absolute rules and our messy, real-world experience. In short, it makes logic tough. It makes it resilient.
So I want to leave you with this final thought. If we can re-engineer something as fundamental as logic itself, to not just survive a paradox, but to actually use it, to learn from it, what other unbreakable rules out there are just waiting for a new perspective? In science, in philosophy, maybe even in our own day-to-day thinking. If we can make logic flexible, what else can we rethink?